Hi folks, in this video we are going to be talking about wave superposition with two-dimensional waves. So we saw in previous videos that waves constructively interfere and they add together to get an increased amplitude when the path length difference is an integer multiple of the wavelength of the waves that are interfering. We also saw that waves destructively interfere, that is, their amplitudes subtract, when the path length difference is a half integer multiple of the wavelength of the waves. So the question we want to answer in this video is, how does this play out for two-dimensional waves? The picture we have here, the blue rectangle, is supposed to be a bird's eye view of a pond. And I want us to imagine that at this location right here, I start tapping on the water. And each tap, a wave is going to ripple away from that source. And as I keep tapping, more and more waves are rippling out. And the picture starts to look, the picture starts to look more and more like this. And I'm tapping at regular intervals so that the spacing of the waves stays consistent, as best as I'm able to draw it. Let's say then that my friend at the same time, I'm going to grab a purpley color here, starts tapping right here with the same frequency that I'm tapping. And so their waves leave with the same wavelength as my waves. And that's what the picture looks like for their waves. Something like this. And so we get this picture overall, this interference pattern that we see here. And my question is, when my red waves and my friend's purple waves meet, at what points will we have constructive interference? And at what point will we have destructive interference? I'm now going to erase the pond so we can annotate this further. All right. So, grabbing my highlighter tool, I want to consider this point right here. Let's call it point A, where the two wave crests intersect. The lines here represent the wave crests, the peaks of the waves. Should have mentioned that. All right. Now, if I'm looking at the red waves, waves, point A is 1, 2, 3, 4 wavelengths away from my source. I'm going to label my red dot S1 for source 1, and the purple dot for my friend is S2 for source 2. We can see that point A is 4 wavelengths from source 1. Now, let's look at source 2. It is 1, 2, 3, 4, 5 wavelengths from S2. What is the path difference for this wave? That path difference is delta L equals 4 lambda from source 1 minus 5 lambda from source 2, or overall 1 lambda. 1 is an integer, and therefore we have constructive interference at point A. My water wave would have a very high amplitude there. If this were a light wave, it would appear very bright. Now, let's do the same thing, but let's consider a different point. I'm going to do my best to erase these highlights without erasing the actual lines. I may not be very good. Give me just a moment to do that. Should have practiced this ahead of time. Oh well. There we go. We got rid of those. Undo. Well, actually, that'll work. That'll work for us. Let's now look at point B, which is right here. point B, how far away is it from source 1, the red sources? The yellow goes out to 4. Now we're at 5. Now we're at 6. So for point B, we are 6 wavelengths away from source 1. How about source 2 now? Looking at source 2, we are 1, 2, 3, 4, 5, 6, and we're not quite at 7. We're actually in between. So we're actually 6.5 wavelengths from S2. What does that mean about our path difference? That means the path difference for B is 6 wavelengths from S1 minus 6.5 from source 2, or 1/2 wavelength overall, which means that at point B, that will be a point of destructive interference. If this were our water wave, we would actually see no amplitude of wave at that point. It would be perfectly still there at that point. For a light wave, that means we would have darkness. Let's do one more point. Let's look at the point that is right here, point C. Actually, I want to do, I think, this point C. All right. Point C, how many wavelengths is it from source 1? Well, the yellow highlights already go out to 6 wavelengths, and it's not quite at the 7th wavelength yet. And so we are 6.5 wavelengths from source 1. That same point C, what about source 2? Well, here we're 1, 2, and not quite yet at 3. So we're 2.5 from source 2. Oh, need to get my color coding right here. We are 2.5 wavelengths from source 2. And so if we find the path difference here, that's 6.5 wavelengths minus 2.5 wavelengths. Forgot my lambda there. There we go. 6.5 minus 2.5 is 4 wavelengths. That is an integer, not a half integer. That's a whole integer. And so we get constructive interference there. Why do we get constructive interference at point C? It's not on a line, but it is where two troughs meet. So we have trough and trough meeting, which gives us a really large amplitude in the downward direction into the screen. If this were a light wave, we would see a very bright point at point C, because we're at the point where trough meets trough. All right, so that is looking at wave interference and when waves constructively and destructively interfere when we are considering two wave sources for waves that are two-dimensional.